All right, let's start. So it's a pleasure to welcome Marina Ansanelli to our seminar. Marina is a PhD student at Perimeter Institute, and she's interested in causal inference, classical and quantum, and that's also roughly the topic of today's talk. New insights into causal inference from the point of view of a quantum physicist.
Oh, hey everyone, thank you for coming. Yeah, I'm Marina, and I'm gonna talk a bit about causal inference, which is this area that was born, like, related to physics. It was born out of machine learning and statistics, like literature. So I'm gonna start by giving you a motivation for why do we care about it in statistics and later in physics. I'm going to start with a super silly example. So imagine you're in a city where you see that there's a positive correlation between ice cream sales and sunburn hospitalizations. Does it mean that ice cream causes sunburn? Of course it doesn't, because correlation does not imply causation. In this case, it's very easy to see what's actually causing both things. It's just like the temperature. If it's hotter, more people get sunburn and more people buy ice cream. Since this data about the heat or sunniness or whatever was not collected, like we only had data about the sunburn hospitalizations and the ice cream sales, we're going to say that the heat is a latent variable. It's a variable that's also important for our causal explanations, but that did not appear in our original data. Okay, so now some notation. I'm going to represent those causal structures as directed acyclic graphs that I'm going to keep saying DAGs. I'm going to represent the visible variables in white, with white background, which are the variables that actually appear in our data, in our probability distributions. And the latent variables that don't appear, I'm going to represent them with gray background. And what does it mean for a probability distribution to be explainable by a certain causal structure? Like, if you see some data, what does it mean for it to be explainable? This is what it means. So here I say a probability distribution obtained from passive observations. What I mean is just that we're going and looking in society and getting some data. We're not intervening on the experiment. I'll go back to this point later. It's realizable by this DAG if it obeys this kind of expression, where the probability distribution, it's factorized as always children given parents, where the parents are the things that point to. So you can see here it's A given C lambda, because it's a child given its parents. Then B given C given lambda, and just P of lambda by itself. And since lambda is a latent variable, like the variable that does not appear in our observed data, we marginalize over it, okay? Everything's classical here. This expression might be a bit hard to check if you only have access to the observed data, which is P of ABC. What we actually want to do is to do some quantifier elimination on this equation in a way that we get rid of lambda from the equation, and we get some constraints that involve only P of ABC. In this case, it's very easy. The constraints is just one. It's just that if you know what is the value of C, so if you condition on C, A and B become uncorrelated. So this is the only constraint that is imposed by this causal structure. But in more general causal structures, you could have more complicated constraints, as we're going to see later. Okay, so this has a lot of applications in classical data analysis in many different situations. And, but why do we care, right? Since we are physicists. So I'm going to talk about in quantum physics. Imagine now that you have this DAG, where you have 4 visible variables, 1 latent variable. Again, as before, the condition for a distribution to be realizable by this DAG is this one, is children given parents and marginalizing on the latent node. And then if you do the quantifier elimination that I said before to get the constraints on the observable distribution, the constraints you're going to get are this. So you have the no-signaling constraints, right? That A cannot depend on Y when you already conditioned on X. But which are kind of like the constraints I showed before. They are conditional independence constraints. It's like condition on something, 2 other things become independent. But you also have more complicated constraints. They're Bell inequalities. An interesting thing here that I want to say is that even if Bell had not done his work in physics, if you are just a classical causal inference statistician, and you start from this DAG, you would get this set of constraints, right? But what we know is that Bell inequalities are violated by quantum mechanics and by experiments, so this DAG is not a good causal explanation for what's happening in a quantum experiment. That's what we learned. Okay, now, if we still want a causal explanation for what's happening in the experiment, then what can we do? The first thing we can think about is, let's change the DAG, right? Let's add more arrows, for example. So here are 3 examples, but all of them have problems. First thing is that all of them violate some metaphysical assumption that we like. So the first one has causation outside of the light cone. This does not necessarily imply signaling outside of the light cone, but I can talk about the difference later. The second one has superdeterminism, so you're not free to choose your settings. And the third one has retrocausality if you assume that the choice of setting in a Bell experiment is made after we made the preparation. But these causal explanations, they also have another problem. And the problem is, the original one, that was just the Bell DAG, where there was no arrow here. If you remember, the set of constraints of that DAG included the conditional independence constraints that are the no signaling relations. But this DAG doesn't. So this DAG, in principle, could give us signaling from X to B. So if you are someone that believes that this is the correct causal explanation, for example, if you believe in Boltzmann mechanics, then you believe that this is the correct causal explanation because Boltzmann mechanics is a non-local hidden variable theory. So if you're a Boltzmann and you tell me that this is the DAG that explains the quantum experiments, you need to tell me why is it that nature hides the signaling from us, right? Because in principle, the causal explanation could allow for B depending on X, but because of some very specific choice of parameters that you do here, by parameters I mean the functions from parents to children. So by some very specific choice of parameters, this correlation is kind of hidden from us. So basically, the problem with these causal explanations, another problem with these causal explanations is that they don't explain why we never saw signaling in the laboratory. So we say that all of them have fine-tuning. Fine-tuning just means that you need to choose the parameters very specifically to hide this correlation from us. So if you believe in this causal explanation, you need to give me more explanation for why is it that nature chooses the parameters so finely. You mean Boltzmann mechanics? Yeah, so in Boltzmann mechanics, you have this thing that you need to start with the row. I don't remember the details, but the fine-tuning comes from the fact that the initial conditions have some equal 0 and some... and they then, like, you might want to ask for an explanation for why is it the case, right? They have some theories, I think Valentini had some theories involving like that with time you have some thermalization, blah, blah. Yeah, I don't know the details. But I'm just saying that if you believe in one of those causal explanations, you need to give me one extra explanation for why is it that nature is fine-tuning. Just this. And then what's proven in this paper is that every classical causal explanation that can violate Bell inequalities is fine-tuned. So these are just 3 examples, but everything else is also fine-tuned. So what else can we do if we don't want that? We don't want to violate those assumptions, and we also don't want fine-tuning. I'm going to change the definition of how causality works to go to quantum causal models. So here, just remember the original definition of what it means for a probability distribution to be explainable by the DAG is this factorization. And now I'm going to change this definition for this factorization. Now, I have this quantum causal model where the latent node is now associated with a quantum system and not a classical or variable anymore. And I just have Born's rule here. But the important thing is that in any causal structure, now it's going to follow the same structure of parents given children. So rho is kind of the system that this thing is going to be in. Sorry, the state that this quantum system is going to be in. And then here you have a POVM that the output of A depends on rho, but it also depends on X, but it does not depend on Y or B. And then the output B depends on Y and also depends on rho. So it's the same structure, but it's different objects. Okay? And this is how we're going to do quantum causal models. And then this kind of solves the problem in a certain sense, that it can explain the violation of Bell inequalities without fine-tuning. So we are being conservative with the structure, but radical with the definition of causation. Okay, so then we mean that this causal structure has a quantum classical gap, which just means that there are probability distributions that can be explained in the quantum version, but cannot be explained in the classical version. I just restated Bell's theorem in a different language. Why is this interesting at all? That's because there are other causal structures that also have quantum classical gaps. And here are some examples that people know. And then with this, it's interesting that we can attest for non-classicality in different scenarios and maybe find different applications of this. Okay, so now I'm going to, this was the motivation. Now I'm going to change topics and ask, go more specifically towards the questions that I'm going to ask in the projects that I'll present. So the question I'm going to ask is, does the treatment cause recovery? So again, imagine that you go to society and you see that the more people that take a certain treatment, there is some positive correlation with these people recovering from the disease. But does this mean that the treatment causes recovery? Or is there some common cause, like health awareness? The people that are more health aware are more likely to take this treatment, but they're fitness, so they would recover anyway. And I'm going to abstract this away as just a generic latent variable lambda that can have any cardinality, because now it can include other common causes more than just health awareness. And then the question is, am I in this causal structure or this causal structure? As it turns out, if I only have this data from society that I got, it's impossible to distinguish between those two causal structures, because both of them can explain any correlation between treatment and recovery. So we say that they are observationally equivalent, which just means that they are indistinguishable if you only have access to passive observations. So what do people actually do to solve those problems in real drug trials? Is that they don't just look in society, they actually do those randomized controlled trials where you force a certain group to take the drug and force another group to take the placebo, and they're not choosing it. So if they're not choosing it, you're breaking the causal arrow from the latent variable to treatment. And then this is what you have now. I intervene on treatment, so I am going to force the person to either take it or not. So I broke the causal arrow here, and now they're distinguishable, because if I still find a correlation between treatment and recovery after that, I know there's actually a causal relationship. Now the question that I'm going to ask is, oh, sorry. Before that, I'm just going to give you some motivation to why we study interventions also for quantum physics. I'm not going to explain exactly how, but in those two papers, they show how to leverage interventions to also detect quantumness. I'm not going to explain the whole thing, but I'm just going to say one thing that with this technique you can do, but you cannot do without it. That is, in the instrumental scenario, that's this one, if we only have access to passive observations, we can only detect quantumness, there's only a quantum classical gap, if the variable x has cardinality 3 or more. But if you also look at this interventional data, if you look at both the interventional and observational data, what these papers showed is that you can detect quantumness even when the cardinality of x is 2. So there's a little bit more that you can do. And it's just a motivation for us to study interventions in general. But the question I'm actually going to ask is this one. The first one, when is it impossible to distinguish two causal structures even when there's access to interventions? And the second one is, when we only have access to passive observations, what can we still learn about the causal structure? So the treatment recovery case I showed you is an extreme case of both questions. Because in the first question, it's definitely possible to distinguish when you have access to interventions. And the second question, if you only have access to passive observations, you learn nothing. But here I'm going to ask you more general causal structures, what can we learn? I'm going to start, everything I'm going to talk about now is in the classical case. And I'm going to start with a result from this paper that talks about the passive observations case. So this result is that we're going to do some very small modifications to the graph structure. And the paper showed that these modifications, they keep observational equivalence. So those are indistinguishable if you only have access to passive observations. The first modification is very trivial. It's just like, here I have a latent node that points to only one variable, but this variable already had a latent node anyway, so I can just absorb them together. So here I'm going to say I'm removing redundant latent nodes. Second thing, here I have a latent node that has a parent. So what I'm going to do is I'm going to take all of the parents of this latent node and send them directly to the children. And now this latent node becomes redundant because it only has one child. So I'm going to remove it. And then I go back to the graph in the middle again. Here I'm going to call this exogenization, which is basically just making latent nodes parentless, like exogenized. So this one in the middle is kind of the most simplified graph out of these three. And they're all observationally equivalent by the result of this paper. And then this paper also introduced a graphical structure to encode all of these observational equivalences that come from these two rules. This graphical structure is called an mDAG. It has some like mathematical structure, but I'm not going to say what it is. The important thing here is that every time you see an mDAG, you just remember that it is associated to a series of DAGs, but the simplest one of them is always such that like this circle in the mDAG, you can imagine it's just a latent node pointing to the variables that are inside the red loop, right? Which is just this one here. So here I have another example of 3 different causal structures that are all observationally equivalent because all of them correspond to the same mDAG. This is the simplest one, this is the one with a redundant latent node, and this is the one with a latent node that has parents. But then with those rules, you go to the simplest one, you go to the mDAG. Okay? In the rest of the talk, you're going to see a lot of mDAGs, but every time you see the red loop, you just imagine it's a latent node there pointing to the visible nodes. Okay. Now, just a side note, in the quantum case, so in the case where the latent nodes are quantum, but the visible nodes are still classical, 2 DAGs corresponding to the same mDAG does not guarantee observational equivalence. So in this paper, there's a counterexample. Those 2, they correspond to the same mDAG, but there is a distribution that can be realized here and cannot be realized here. I'm not going to go into too much detail now, but you can ask later if you want me to explain this counterexample. But that's just a note. So back to the classical case. Now I'm going to ask, what about when there are interventions? I told you that if they correspond to the same mDAG, they are observationally equivalent. But what about when you have access to interventions, in fact? That was our first question. And then this is what we did in this paper with Rob and Ellie. And what do I mean by having access to interventions? I'm going to start by establishing that. I'm going to define a probing scheme that I call observe and do probing scheme. This is a probing scheme that's very powerful because it's as follows. You first are going to ask what is the natural value of the variable, which I'm going to call a flat. So the natural value is just like what value the variable will take normally. But then you force the variable to be something else. But you record both the natural value and the value you forced. So in the drug trial, for example, this is as if you come to your patient, your subject, and then you ask them, do you want to take the drug or not? Then you write it down, and then you ignore what they said, and you give them the drug or not, regardless of what they asked. And then in the end, you get this probability distribution over both a flat, that's the natural value, other variables, and a sharp, that's the thing that you forced. And if you do this to every visible variable, you have this observe and do probing scheme. So you see, this is a very strong interventional probing scheme. That's stronger than what people usually do in the laboratory, because they usually don't ask first. So so here we wanted to give a probing scheme that's as strong as possible. And we give some argument as to why we think this is like informationally complete. This is like everything you can learn about the causal process. And then what we found is that if 2 causal structures correspond to the same mDAG, they are indistinguishable even under this super strong interventional probing scheme, which is very cool. Like, that means that the mDAG is really a fundamental object if you want to study classical causal inference, because you don't ever need to start from two candidate causal structures that correspond to the same mDAG, because you know they're going to be indistinguishable. Doesn't matter what experiment you do, basically. And this is if and only if. If they correspond to different mDAGs, then this probing scheme can distinguish them. Okay, so that was very cool. And another cool thing is that this shows that the difference between the quantum and the classical case is even bigger than we thought. Because in the quantum case, as I told you, you have two causal structures that correspond to the same mDAG, but they are not, even observationally equivalent. But in the classical case, I'm telling you that for any experiment you do, they're going to be equivalent, not only passive observations. Okay? So do you have any questions so far? Is everything okay? No, we don't yet. Okay. So the next question we asked is, can we weaken the interventional probing scheme and still be possible to distinguish between causal structures that correspond to different mDAGs? So here the direction of the implication is like this, is to show that two causal structures that correspond to the same mDAG are really indistinguishable, you want the strongest possible probing scheme, right? And then you're like, wow, even under the super strong, it's indistinguishable. Now, to show that you can distinguish if they correspond to different, then you want the weakest possible, right? Because you're like, even without much power, you can already distinguish them. So that was the question now. We know that for the super strong one is if and only if, but what about weaker probing schemes? So we defined, so this is, as a reminder, the strong probing scheme we had, where you ask and then you force. Now, let's think about one that's slightly weaker. That's more closer to what people actually do. That's you don't ask the natural value. You just do a do intervention, you just force. So the data we have now doesn't have the A flat, only have A sharp. And then I'm going to do this. It's called all patterns, because I'm going to do this intervention. I'm going to collect like a big tuple of data with these interventions for every subset. So I have this data where I observed B and I intervene on A. This data where I observed BC, I intervene on A. This data where I observe A, intervene on BC. So if I have this big tuple, so it's still a strong probing scheme, but it's weaker than the previous one. And this is already enough to distinguish two causal structures that correspond to different mDAGs. Furthermore, this other even weaker probing scheme that's called observer one do, because now I only allow for, like, I'm only allowed to force the variables to take one possible value. One example here would be, let's say, if you want to know if smoking causes cancer, it's already a bit sketchy to force your patients to stop smoking, but forcing them to start smoking to see if they'll develop cancer is even worse. So let's say that you do an experiment where you can force them only to stop smoking. So you only have the power to make the smoking variable to 0. You don't have the power to force it to 1. And then even in this situation, that's already enough to distinguish any two causal structures that can that correspond to different mDAGs. Right, yeah, so there is, okay, so the thing is that you need to look at, this is like this all patterns observe or one do. So you again need to look at the case where you intervene on A, and then what happens with B, the case where I intervene on B, what happens with A, the case where I intervene. So you have this big tuple. If one of them you don't get like a value, it's okay, because you need actually a lot of data. What I was saying is that you're saying that, for example, if for A sharp equals 0, okay, then I don't know. I think I don't really understand the question. I know, but here we are forcing the thing to take that value, right? So I'm just saying, in a situation where you can only force it to take one value, even if that was not in the original observational support. So let's say if nobody in the world smokes, or like nobody in my sample smokes, so in the original distribution, smoking is not in the support, but I can still force one patient to smoke, right? And then, now, this is the intervention. Yeah. Yeah, but as I said, it's still quite strong probing scheme because you need to do this for every subset of variables. So like, for A, B, you're gonna force them to something, and then see what happens with C. For A, C, you're gonna force them to something, see what happens with A. So, yeah. Any other comments or questions? No? Okay. Yes. No, you don't really need that. Yeah. This is just like to distinguish the causal structures themselves. So, yeah. Here I just mean that there's gonna be, okay, so fine tuning is about one specific causal mechanism that gave me my data. But here when I say that those causal structures are distinguishable, what I mean, like, not those, sorry, two different causal structures are distinguishable. What I mean is that there is one set of data that's realizable by this causal structure that is not realizable by this one. So that's not necessarily the set of data I'm gonna see in the laboratory. So it might be that in the laboratory I'm still ambiguous. But I'm saying that those causal structures are not in principle indistinguishable. Okay? But if they correspond to the same mDAG, then they are in principle indistinguishable. I'll never see any data in the laboratory that tells me a difference. Exactly. If everything is uncorrelated, any causal structure explains it. Okay. Make sense? All right. Then, so in summary, this is what we found in this project, that those three different probing schemes, they're all characterized by mDAGs, in this sense that it's indistinguishable if and only if same mDAG. But passive observations is not. So as I told you, in the classical case, same mDAG gives you equivalence under passive observation, but the other way around is not true. Like different mDAGs does not mean observational distinguishability. So that's the next question that we're gonna ask. That's question 2. When you only have access to passive observations, what can we still learn? So that's what we did in this other project, also with Ellie and Rob. And basically, the idea is this thing I said, that different mDAGs can still be observationally equivalent. So here are 3 different mDAGs. All of them, as I said, if you have access to those powerful interventions, all of them can be distinguished. So there is some set of data in one that is not realizable in the other. But if you only have access to passive observations, then there's no way to distinguish them because the set of constraints on the observed probability distributions of these 3 DAGs is the same. It's just this, that when you know B, A and C become uncorrelated. So then we want to know, like in general, how can we find equivalence classes of mDAGs under this observation equivalence, or even more, a partial order of these equivalence classes. So I'll show you the simplest example with 2 nodes. You have 2 equivalence classes, one that has no constraints, this can explain any distribution, and one that has one constraint that is just like factorizing, so they're independent. This is like the treatment recovery case that we had in the beginning, right? And then here, the partial order is very simple. Now, just a small caveat, I'm only putting causal structures where here A comes like temporally before B. So this is why I'm not comparing with B points to A. But I can talk more about this later if you want. All right, so what we did in this project is that we gathered from the literature all of the rules that are currently known to show observational equivalence between classical causal structures. We also proved some new ones. So here I say observational dominance and non-dominance because what I want is actually to construct the partial order. So dominance just means the set of distributions that's realizable by this causal structure is a superset of the set that's realizable by this causal structure. So then with this analysis, like gathering all of the rules from literature, and we have that for the case of 3 visible nodes, we have this diagram that's a bit hard to see. So again, remember that every time you have these red loops, it just means it's a latent variable pointing to the guys that's inside the red loop. Again, in the top, we have a saturated class. That means I can explain any probability distribution. And then we have all of the other DAGs with 3 visible nodes. Cool. And this is a complete solution. So this is the partial order we completely found it. Why is this useful? So there are a few reasons why you would want to have that. Usually, in the causal discovery problem, we start with a probability distribution that we got from the laboratory over a certain set of visible variables. And we want to know what is the causal structure that causally explains it. If you have something like this, then, for example, if I check that it's not this causal structure, I don't need to check this one, because they are equivalent. So I reduce in a lot the number of things I need to check. More than that, I don't need to check anything that's below, because what's below is just going to be strictly weaker. So if you cannot do it here, you also cannot do it here. So if you have a probability distribution, you want to know if it's compatible with, like, you want to find what is the possible candidate causal structures, you can start from top to bottom. So top is always, like, saturated is always going to explain everything, but then you go below and see what is the one that explains better. And this might be useful, for example, for people that work on on network non-locality, because many times these people have some probability distribution that you found in a certain causal structure from a quantum strategy, but you want to know if this probability distribution is really like a test quantumness, or if it's also realizable by a classical strategy in the same causal structure, right? And then these types of techniques to finding if a probability distribution is classically explainable in that causal structure or not can also be helpful for that. Okay, other reason why this is interesting, it's because there was a paper recently that showed that a causal structure, okay, so before I mentioned to you that the causal structures have different condition independence constraints that they impose on the compatible probability distributions, like the non-signaling constraints. But there are also other types of constraints, like the Bell inequalities, right? And there are causal structures that also have other causal structures, not just Bell, that also have inequality constraints. And these are important for us because inequality constraints are the only ones that can be violated quantumly. The equality constraints, like, for example, the conditional independence ones, the non-signaling, blah, blah, they are also valid when the latent nodes are quantum. And in fact, they're also valid when the latent nodes are any GPT. So if you want to distinguish any 2 GPTs, yes? No, that's a theorem. Yeah. Yeah, so if you want to distinguish, like, if you have a causal structure, you want to distinguish any 2 GPTs, but in this case, be it classical and quantum, you need to, first thing you need to know is that your causal structure has inequality constraints, because if it doesn't, then you have no hope. Also, from the point of view of classical causal inference people, inequality constraints are usually much harder to characterize than the equality constraints. So it's also good to know if there's going to be inequality constraints, so you know if your problem is going to be easy or hard. And recently, there was a theorem that proved that in a classical causal structure, you have inequality constraints if and only if you are not observationally equivalent to a causal structure that does not have latent variables. Basically just means that you can look at the equivalence class, and by looking at the equivalence class, you know if it has inequality constraints or not. And with this result, that's the result I mentioned, we know that the causal structures that have inequality constraints are those 5, and these are all famous ones. So this is the triangle scenario, if you already heard of it. Those 3 are different versions of the instrumental scenario, and this is called the Evans scenario or the unrelated confounding scenario. And in fact, all of them have quantum classical gaps. The triangle instrumental is already known for some time. The Evans, it was proven like this year, I guess, or last year by a group. And that's very cool. So for the case of 3 visible nodes, we know all of the causal structures that have quantum classical gaps, and they are exactly the same set of causal structures that have inequalities. But in general, we don't know if every time there's an inequality, there's going to be a quantum classical gap or not. Okay. Yeah, that's a good question. I guess that yeah, I don't know. Good question. Yeah, I guess that here, like, if you have less structure, this is basically just the two node ones where none of them have inequalities, right? And one disconnected thing. But yeah, I don't know. Maybe we should check that in the 4-node case. I didn't really look at the picture. That's what I was going to talk about now, the 4-node case. But before that, just note that it looks like they're minority, right? The inequality ones. Like you have a lot of equivalence classes, but then it looks like inequalities might be rare. But in the 4-node case, at least 85% of the equivalence classes have inequalities. They're actually very, very common. And just 4 visible nodes, which is a very small number of nodes, actually. Like the mDAG is in here. So, okay, we applied all those rules for the case of 4 nodes. The total number of mDAGs is this very large number. We did not get a complete solution yet. So here, that's a mistake. It should be lower bound here and upper bound here. Sorry. But we did not get a complete solution because the lower bound is still not the same as the upper bound on the number of equivalence classes, meaning that there are still cases of 2 causal structures with 4 nodes, 4 visible nodes, that we don't know if they're observationally equivalent or not. But you see that doing this work is already like very helpful for the problem of like finding what is the causal structure that explains your data, because you go from 7,000 to 1,000 something. So it's already good. And it's very cool that even without having a complete solution, we know that the inequality constraints are so common. Okay, so there's like a huge potential for quantum classical gaps, and yeah. Another conclusion we got from this work was that we found that some observational equivalence classes, they're such that they can be specified by their conditional independence constraints alone. What does that mean? In general, the equivalence class, like, it has independence constraints, but it also, like this conditional independence constraints, it can have other types of equality constraints, and it can have inequality constraints. But these classes, they have also inequality constraints, but they are the only classes that have this exact set of conditional independence constraints. So basically, I'm telling you that if I tell you that my causal structure has exactly the no signaling constraints, no less, no more, then you know my causal structure is equivalent to the mDAG. Okay? And this is what gives rise to the no fine-tuning no-go theorem back in the Bell case. And why is that? The no fine-tuning no-go theorem basically says that if you have any other causal structure that violates Bell, and therefore is Bell inequalities, and therefore is not equivalent to this causal structure, then it also does not have this exact set of conditional independence constraints. And then what we found in this work is that there are other causal structures, like, for example, the square, where the square is the only equivalence class where the independencies are exactly B independent of D and A independent of C. So all of these admit of a fine-tuning like theorem, just saying that if I find a distribution that obeys exactly these independencies, but it violates the inequalities of the square, which is something that could come from a quantum experiment, for example, then this distribution only admits of a classical explanation if the explanation is fine-tuned. Okay, so we found like what are all of the cases where this is going to happen in the 4-node case, but they're actually rare. Most cases this does not happen. In most cases it's like this, where you have the saturated and the triangle, and the triangle does not have conditional independence constraints. The saturated also doesn't. So this set of conditional independence constraint, that's the empty set, does not characterize what's the equivalence class, because the triangle has inequalities. And when I say most, it's like more than 90% of the observation equivalence classes, which I think is also an important point, because usually in classical causal inference, since people usually they work with DAGs that have many more nodes, finding the equality constraints is already a bit hard. So that's what people focus on the most. Like most of the classical causal inference literature is on equality constraints. The inequalities are the important thing for the physicists, but and of course some like people from the classical community also study them, but that's not the main focus. But I think this result shows that it's important to go beyond conditional independence constraints for causal discovery. Because if you only look at the conditional independence constraints, you can only like single out what's your equivalence class in less than 10% of the cases already in the 4-node case. So who knows what's going to happen after that. Okay, so these are some conclusions that we got from this work. Before I move on, is there any questions or comments? No, yeah. We just found, we gather all those theorems and stuff, and then we just coded them, and yeah. So that's also why I don't have a picture. Okay. Yeah, so now I'm going to just briefly mention that I have other project with those two, like Ryan and Robin, who are statisticians from Oxford, where we're doing the same thing, like finding those distinguishability of causal structures under passive observations or interventions, but for the case where you have direct causation, you have common causes, but you also have selection bias. And that was very cool, but I'm not going to talk more about it. You can ask about it later if you want. I'm also going to briefly mention another project that, another project on these other causal structures that have quantum classical gaps. That's because so far people have known, I don't know, there are a few famous ones that I mentioned already, like instrumental, triangle, Evans, but there are not many different causal structures that are known to have quantum classical gaps. Like, I don't know, I'd say there's like 6, 7 around this number. So then we had another project a few years ago where we're asking quantum classical gaps in causal structures. How do we prove new quantum classical gaps by like piggybacking on cases that we already know? It's kind of embedding cases that we already know in new causal structures. And then we found that most observation equivalence classes of mDAGs with 4 nodes have quantum classical gaps. Here I put most with asterisk because we ran this code too long ago, and then there are many changes and iterations since then, and I didn't rerun it. But I remember it was like more than 60% of the equivalence classes have. So it's like thousands of new causal structures that have quantum classical gaps, which I think was very cool. This was a project together with 3 master students that we were supervising in a small project. So this I also just wanted to briefly mention, because now I wanted to finish the talk by talking about another project. How much time do I have left? 10 more minutes. Oh my god, okay. Okay, sorry. Which is this project, where we were estimating probability of causal dependencies in causal structures. Janani and Bessie, they are also 2 master students at PI that we were supervising in another project. And the question here is, so far, I was asking what is the causal structure that explains my data. Now, I'm going to assume I know what is the causal structure. And I want to learn about the actual functional dependencies between the variables. So what do I mean about these functional dependencies? If you imagine the simplest case where you only have x and y, before I was showing you the factorization, like in terms of parents given children, but this is equivalent to saying that the children are a function of the parents. So here in the simple case of x and y, and they're both binary, like they both only take 2 values, I have 4 possible functions. It's either identity, where y copies x, y flips x, or y ignores x and resets to 0, or resets to 1. So those are the 4 possibilities. And for a distribution to be compatible with this causal structure, a different way that I can write the same condition I had written before, it's like this, where now I have a delta over y being a certain function of x, and I have this thing which is my probability distribution over functions. It's like, what is the probability that the function is identity? What is the probability that the function is flip? This is the same thing as the factorization I was showing you before, but now more explicitly in terms of the functions. Now I'll show you a same thing but for slightly more complicated case. This is the instrumental scenario. So here you can see that you're going to have a delta of x being a certain function of z, of y being a certain function of x, and I have a joint probability distribution over those 2 functions because those two functions, I'm going to say they're determined by lambda. So lambda is going to say how does x respond to z and how does y respond to x, but in a correlated way. This is why it's a joint probability distribution. Okay? And this is the thing I'm gonna want to estimate. Like I'm gonna want to learn things about what is this probability distribution over functions. And we can argue later, but we believe this is the best way of quantifying causal influence, if you want to quantify causal influence. Okay, so I'm going to give you an example. This example is an example where from the observational distribution, I can learn everything about the underlying parameters, like functional parameters of the causal model. So I have this causal structure, and then in this distribution, I have that y is perfectly correlated with z. So when z is 0, y is 0. When z is 1, y is 1. But x is uniformly distributed and ignores y and z. If I know this is the causal structure and this is the observational data, I immediately learn that these are the functional dependencies. So lambda is going to be uniformly distributed, and it's going to decide whether the functions are identity and identity or flip and flip. Does it make sense? It's because if there was a reset to 0 somewhere, then there's no way z would be perfectly correlated with y, for example. And then I can have like z being 0, then flip 1, then flip again 0. So if it's flip, flip, I'm going to have perfect correlation here and uniform distribution here. If it's identity, identity, the same. And since I have half, half here, I know that lambda needs to be uniformly distributed in half, half as well. So this is a specific case where from the observational distribution, you can learn everything about the causal parameters. But that's a very particular case. And because of this idea of seeing what you can see observationally and learning everything about what's underlying, we can like make just a crude analogy and say this is kind of classical self-testing. Right, yes?
So you always assume that you know the support of your distribution. For example, if these are binary variables.
Yes.
Yes. And going just connected to that, back to an earlier slide where you talked about the inequality constraints.
Mm-hmm.
So when I think of a Bell inequality, then it's true regardless of the support of my probability distribution.
Mm-hmm.
Sort of. Okay. So when you talked about inequality constraints there, were you also referring to a case where you know the support of the cardinality of your variable?
So when you say that the Bell inequalities are true regardless of the cardinality, you're saying, because like if you only have binary cardinality, you only have the CHSH inequality, but if you go beyond, you have more Bell inequalities that are more complicated. Right. So what exactly do you mean?
Good point, I have to rethink that. I'll get back to that later.
Okay.
The idea that the Hilbert space dimension doesn't matter.
Ah, okay.
Separate thing.
I see. Yeah, no, here I'm talking about on the classical side only. Yeah.
Okay,
All right, so then this is an example where you can perfectly determine, but in general you cannot. In general, you can only find bounds. And then that's what we did in this project. We were finding those bounds and like seeing what can we learn about this probability distribution over functions, which we argue is the more fundamental object to learning about the causal model. So here I have an example. So I would like to tell a story for this example. The story is, imagine you want to know if smoking causes cancer or not. And then X is smoking and Y is cancer. But if you only have X and Y, you cannot distinguish between the two causal structures, right? Like imagine you don't have Z. It's the same thing as the treatment and recovery I said before. So you cannot distinguish. But now you also cannot do an intervention because let's not force people to start smoking or stop smoking. So then what can you do? Is there any way of distinguishing those two causal structures? And the answer is yes, by finding a third variable that we call an instrumental variable that only influences smoking, that you assume only influences smoking. So let's say that lambda is like a gene, like, I don't know, the cigarette company comes and says, cigarettes does not cause cancer. It's because there's a gene that makes you want to smoke and it makes you develop cancer. And then you're like, okay, even if I allow for that cheap explanation, I still think there is a direct causation. So how can you distinguish between those two? You find this third variable Z that only influences smoking. So let's say your peer group Like if you hang out with smokers, you're more likely to smoke. But we're going to assume this is not influenced by this specific gene. And we're going to assume that it does not influence cancer directly. Then you can distinguish those two causal explanations. And that's because if you find a correlation between peer group and cancer, any correlation, then you know that this arrow is there. Because this causal structure is such that it has this independence constraint. Like there's no causal path between Z and Y. So Z needs to be independent of Y. And this is called the instrumental variable technique, and this actually got a Nobel Prize in economics like recently. Yeah, it's super, super simple. Yeah, I think so. I mean, yeah. Yeah. Yeah, but it's fun, no? Yeah. Okay, so, all right. Now I'm going to ask the quantitative question, like how much does smoking cause cancer, right? So I want to know, like, what is the strength of the causal influence from Z to Y? I can bound it based on how much this equality is violated. And then, like, what we found is that if you take the probability that the function from X to Y is identity plus the probability that is flip, so it's the sector where you have causal influence. The other two possibilities were reset to 0 and reset to 1, meaning no causal influence. So if you take this probability that you are in the sector with causal influence, we found that this is lower bounded by basically this thing that measures how much Y is correlated with Z, right? Because if, like in the special case we had before, where Y was perfectly correlated with Z, you have that this is 0, this is 1. So you definitely are in identity or flip, as we have found before. So you can use this equality constraint to bound the strength of causal influence. And how is this related to everything I was talking about previously in this talk? Note that this causal structure observationally dominates this one, because there is one constraint in this one that's not there. So if you look at the image I had before, they are these two. And as it turns out, every time that removing an arrow takes you out of the equivalence class, you can use the violation of that inequality to kind of quantify how strong is that arrow, or at least learn things about the probability distribution over functions on that arrow. So now let's see other example, like compare this with this. Now the instrumental scenario does not have any, oh, sorry, did you? Okay. The instrumental scenario does not have any equality constraints, but it has inequality constraints. So I'm comparing this guy that's saturated, has no constraints at all, with this guy that has some constraints, for example, Pearl inequalities. This Pearl inequality, it basically says that if Z is fixed to 0, then you have a limit on how much Y can be if X is fixed to 0, then you have a limit on how much Y can be correlated with Z, because basically the correlation passes through X. But here you don't have this limit, because you can have direct causation here. And then what we found is that the violation of this inequality, gives me a bound on the probability that the function from Z to Y, when X is 0, is identity. Okay? So the more I violate this inequality here, the more weight on identity I need in this red arrow. One interesting thing that we found that we didn't expect before, like we had this intuition that you're going to quantify the arrow, that's the arrow you remove. But one interesting thing we found is that you can always learn a few things about the other arrow, the arrow from Z to Y. So here I'm learning a few things about this arrow. But now I don't have a lower bound, I have an upper bound on certain combinations. So the more you violate this inequality, the less you can have here of certain combinations of the probability distribution over functions. More specifically, when Z equals 0, you cannot have too much flip on X to Y, which kind of makes sense if you look at the inequality, because when Z equals 0, this inequality kind of says that if this number is big, it says that you have a lot of X being equal to Y. So then you cannot have too much flip. And then the same thing here, when Z equals 1, this inequality, this thing being big, this quantity being big, is going to say that you want Z to be different than Y, so you have a limit on how much identity you can have. So yeah, with this way we can use those violations of constraints, both equality and inequality, to learn things about the underlying functional parameters. And yeah, that's what I wanted to talk about. So thank you.
Thank you. Are there any questions? Jan?
Thank you. That was really nice. I have two questions. So in your models, the sample spaces, they're always binary. Is that right?
In this last case, like you mean in this last project that I don't know how to change the slides anymore. Yes. Yeah, so here in this last part, yes.
Yeah, but you can relax this.
Yes.
You have these function spaces and stuff.
Yes. It's just because we, so far we only looked at the binary case. When you relax this, I think one thing that we need to solve is, because I kind of said that this thing, the probability of identity plus probability of flip, is kind of my measure of the strength of causal influence. I can either say, oh, I'm just learning things about the probability distribution over functions. But if I want to give a measure of strength of causal influence, then if I have higher cardinality, I'm going to have to put some weights, right? Because like certain functions are going to have more causal influence than other functions. Right. So it's something that we need to solve, but we still didn't go there.
Okay, thanks. And if I can have another one, just maybe if you have anything to say about how this thing is scaling. So you mentioned how you go from 3 to 4 and it gets almost impossible. We usually have like much more than 4 variables.
Yes.
So yeah, any thoughts about like if you think this can be overcome or you need some different methods?
So I think that right now, okay, so like to get this partial order, you mean, right? The functions, the part of like obtaining all mDAGs, I think we could do it in the case of 5 nodes. But the problem was when we applied the equivalence and inequivalence rules, I think this was very slow when we tried. But we optimized the code since then, so maybe now it's okay. But we didn't really try, actually. So maybe it's possible. But I think after that, like after 5, it's very, very hard. I think it scales very fast. So yeah, like there are many conjectures that we have. For example, the number of causal structures that have inequalities increases with the number of visible nodes. But it's something that we only have evidence for 2, 3, and 4, right? Like we don't have a proof or anything. Yeah.
Right. Thanks.
So I have a question which is however a bit vague, but it's just maybe a piece of intuition that usually when you have these 3 variables like maybe smoking and cancer and so on, then you're part of a very messy world with lots of other variables. Are there some sort of, say, robustness theorems where say, here's my small DAG, actually there are more nodes, but they have only sort of weak arrows coming in, like tiny bits of extra influence, or maybe some underlying shared randomness that goes into everything. So is there anything known about this being still an approximately good description or something like this?
Yeah, so usually when you have some latent nodes in the DAG, you can clump everything in there. So like here, if you say that you have these other things, blah, blah, but you have the assumption that they only influence X and Y, then you can always clump everything in the latent node because everything I do does not assume anything about the cardinality of the latent node. So this thing can be cardinality 1,000. But if you say that you have other things that can also influence like Z, yeah, then it gets much more complicated. And I'm sure like people in statistics have techniques to deal with that. Like to assume that you have causation, but it's a weak one or anything. But I don't know.
Okay, that makes sense. Is it perhaps related to the thing that you really want freedom of choice, for example, in a Bell experiment? Like here you would variable Z maybe not be influenced by lambda, for example, otherwise you can get all kinds of distributions.
Yeah, exactly. So in stuff like in Bell's theorem, we can make like metaphysical assumptions, right? Like freedom of choice and stuff. But in the society things, we just rely on our field expertise. Like we just rely on assuming that things that could influence both cancer and smoking, like this gene or whatever, are not things that would also influence your choice of friends. But that's kind of a fuel assumption you need to make. And I suppose people might have techniques of quantifying like when this goes wrong and stuff. Basically, if you look at this, you can say that this is a way, like this comparison here and the quantification we did, is kind of a way of seeing, okay, what if my peer group actually influences cancer directly? So what if I have this bad instrument, right, that's not really helping me do the... Then I think that techniques like this, where you learn, what can you still learn about the arrow from X to Y? Like you cannot learn as much as you did before, but maybe you can still learn a few things. Yeah.
Yeah, that makes sense. Great, thank you. More questions? If not, let's thank Marina again.
Thank you.